Welcome to LabMinutes.com and our lab video series on MPLS. You can find a complete list of MPLS video on our website by clicking on the link above and sign up for our newsletters to receive the latest video updates. So in this video we will look at how to extend multiple VRF to a CE device so that you can have the CE device being shared among multiple customers. And since the CE device needs to support multiple VRF but would not participate in the MP-BGP, this is considered what is also called VRF-lite, and this is a term that you might have come across before. And we're also going to look at two routing protocols for the PECEs, and those are BGPs and OSPF. For our physical lab topology, we have 8 routers, R1 through R8, and one switch 1 with R2, 3, 4, and 5 connected across 0 point-to-point links, while the other router and switch are connected across the VLAN. With exception to the router R2 and R7, they are connected across 2 different VLANs on their 2 sub-interfaces. And then we have R6 here on the back that's also have a point-to-point link connected directly to the R7. Now moving down to our layer 3 topology, we have our MPLS VPN core here at the middle with R1, 2, and 4 being the PE routers and R3, R5 being the PE routers, and we already have the MP-BGP configuration completed at this point. Now for our customer, we have 2 customers, C1 in green and the C2 in red, and those are the 2 VRFs that we would like to extend to our CE device here, which is our R7. So what's going to happen, we're going to split those 2 customers into 2 different VLANs. For our customer C1 is going to be coming across VLAN 27 between R2 and R7. For customer C2, it will be a VLAN 72 here between R2 and R7. And customer 1 will be running BGP as the PECE, and the customer 2 will be running OSPF for the PECEs. And for the link between R6 and R7, we're going to kind of switch between the 2 customers VRF as we perform a configuration and testing. And for connectivity testing purposes, we have our R8 and switch 1 loopback 10 through 12 advertised into our MPLS VPN, and then we're going to complete the other side of route advertisement using R6 loopback 10 through 12 also. So those are the subnets we're going to use for our testing. So let's begin with our task number 1 with VRF-lite. So we need to configure a VRF C1 with the route distinguisher 100/100 on the router R7, and then add the interface fast00.27 to the VRF. We do the same thing with the VRF C2 with the RD of 200/200, and then we're going to add the interface .72 to that same VRF. Okay, so just a very basic VRF-lite configuration on the router R7. Just to bring up the diagram, so this is the portion that we're going to complete right here, and obviously creation of the VRF. So let me hop over to router R7. First we'll do IP VRF C1, and RD is 100/100. Since we're not really dealing with the MP-BGP, so we don't really need the route target for that. All we need is just the route distinguisher. Next is the VRF C2. And that would be 200/200. Okay, now we're going to add fast00.27 IP VRF forwarding C1, and then we're going to have to put the IP back in, since once you add the interface to be a member of a VRF, the IP information will be erased. So that we want to say to 16.27.7/24. Same thing for, actually this time let me just do show run .72 IP VRF forwarding for C2. I'm just going to copy and paste what we had previously for the IP. Okay, make sure we do a quick connectivity check by doing a ping from VRF C1 to 192.16.27.2. So that would be the interface or sub-interface on the router R2. And then we also ping the interface on the VRF C2 as well. That will be 72.2. Okay, so both of those are reachable, and that should be it for task number 1. Okay, next is task number 2, which is the BGP routing protocols for the PECEs. Specifically for our customer 1, we need to configure BGP session between R2 and R7 with the AS of 65124 across VLAN 27. And then we also need to allow MPLS label exchange and forwarding, and we're not allowed to use LDP for that. Okay, so that would be this connections right here for the BGP. Then we need to add the link between R6 and R7 to VRF C1, and then configure a BGP session across that link between R6 and R7, and we need to advertise R6 loopback 10 through 12. Okay, so that would be adding the interface to the VRF and then create a BGP session between those two routers, and then we need to verify connectivity between R6 and R8 loopback 10 through 12. Since R8 is also part of VRF-C1, so we're going to test connectivity end-to-end between R6 and R8. Okay, so let's begin our configuration on the router R2 side with the router BGP 100. Okay, under the address family, IPv4 VRF-C1. Okay, the neighbor is going to be the interface IPs of R7, so it would be 27.7. The remote AS for R7 is 65124. Make sure we activate that. And in order for the two routers to exchange labels without using LDP, we can leverage the BGP protocols and use BGP advertisement to carry the route labels. And for that to happen, you need to issue a command send label. And since our AS number between the two sites here are the same, we need to make sure that we configure R2 with the command AS override, so R2 will advertise the route to R7 with the same AS number. So that would be AS override. Okay, which you might have seen in our previous lab videos, the use of AS override. And even though that you have the MPLS label exchange, it doesn't mean that the interface on the routers will start forwarding or accepting label packets. So by default, the interface will not accept any MPLS packets. So what we have to do, again, without enabling LDP, and this is on the R2 side, is fast 0/27, you have to issue the command MPLS. You can see right here, there's an option for BGP and forwarding. Right? So that should be it for R2. Before we move away from R2, let's do a quick debug MPLS packets so we have that running. Alright, next we're going to configure the router R7, which is the other side of the BGP, with the router BGP 65124, standard no auto, no synchronization. Give it the BGP router ID 192.16.0.7, which is loopback 0 of R7. Then we get under the address family, IPv4 VRF-C1, since we're going to be communicating across the VRF-C1. I guess it's the part of the VRF-lite configuration. Next we'll define the neighbor, 192.16.27.2, pointing to R2 with the remote AS of 100. Next we'll activate the neighbor. Make sure R7 exchange label with R2 with the send label commands, and that should be it. Okay, so you can see that as soon as you type in send label, the capability got changed between the two routers. And at this point, we should have the BGP session between R2 and R7. So if you do show BGP, IP BGP VPN v4 all, you can see that R7 is now learning routes that belongs to R8 that came across MPLS VPN. Okay, next we're gonna configure the BGP session that faces R6, but first we need to add the interface. Right here, 000:0 to the VRF, so IP VRF forwarding C1, then IP address 192.16.67.7/24. Do a quick ping verification. Would be a .6. Make sure we can ping 67.6. Doesn't look like that we can ping, so let's see what we have configured on the interface. Okay, and now let's hop over to R6 and take a look. Let's check the interface status. So that's up, so there should be no reason why we can't ping. Okay, so that just went through. Maybe we didn't wait long enough, so let's go back to R7 and do another ping. Alright. You can see we can ping across that link now. So now getting back under the router BGP 65124, address family IPv4, VRF-C1, and then configure the neighbor for R6. The remote AS, so this will be an iBGP session 65124. We're just going to keep it simple and use the interface IP, so we're not going to do the update source. But what we also like to do is to use the next hop self command to reset the next hop IPs, and then I'm just going to finish it off with the activate command. Okay, so now if we do show, I think we already did that, show IP BGP VPN v4 all. We have those routes from R8, and we show MPLS forwarding. You can also see that along with those routes we have received the labels. So if I do show BGP and v4 all with the subnet, you can see that coming across the BGP session or advertisement, you see that MPLS label right there. Okay, that's why we do show MPLS forwarding. Look at the forwarding table, we see all the outgoing label for different subnets. Alright, so that's for R7. Now we're going to complete our configuration on R6 by configuring BGP 65124, no auto, no sync, BGP router ID 192.16.0.6. Let's do a network command first. We need to advertise R6 loopback 10 through 12, so let's take a look. So these are the 3 loopback we need to advertise. Use the network command 6600. Those are all /24. So mask is /24. Then that's loopback 11. And that's loopback 12. Okay, then we configure our neighbor command 192.16.67.7 with the remote AS of 65124, again IBGP session. Then we'll give it a second. And we got our adjacency that came up, and we do show IP BGP. You can see that R6 is now learning all the routes that belongs to R8. And now if you're trying to ping from R6 to R8, so right here R6, we're going to try to ping all the way across to R8 through Multi-VRF CEs and then MPLS VPN. Let's ping 8801, which is R8 loopback 10, sourcing from its own loopback 10. You can see those are pingable. Okay, and now if you go over to R2 and look at the MPLS packet debug that we kind of left running, you can see right here the packet that's being received, so RX means it's entering the interface fast 00.27, which is coming in this way, has the MPLS label of 21, 0 being the experimental value, and 254, those are TTL values. So 21, which kind of agrees with what we saw earlier when we did the show MPLS forwarding on R7 right here. Going towards 8800/24, the outgoing label is 21, and we did see the label being 21, and then that's the VPN label. But leaving R2 out of 0000, so that way, in that direction, entering MPLS VPN, obviously there's a transport label that got prepended, and the MPLS VPN label got changed as well, and that's just part of all the label switching. Right here you can see that there are 2 labels that's on that packet. One is the VPN label, the other one is the transport label that gets the packet from router R2 to R1. Okay, and you can double check on that by do a show MPLS forwarding label 18. You can see how it's pointing to R1 loopback 0. And we can also see if we can try to look up label 17. I think it has to be part of the VRF-C1, I believe. Okay, so incoming label 21, and then outgoing will be 17. That's why we saw it. This one is incoming 21, and then outgoing 17. Alright, so that should complete our task number 2. Moving down to our task number 3 with OSPF being our PCE routing protocol. Specifically for our customer C2, we want to configure OSPF area 4 between R2 and R7 across VLAN 72, and then allow MPLS label exchange and forwarding. So now we're going to change our focus onto this VLAN right here that we're going to run OSPF across. That's VLAN 72 and subinterface .72. So we need to enable OSPF area 4 between those 2 routers, and then we need to reassign the link between R6 and R7 to the VRF-C2. And then configure OSPF area 4 across that link, and then advertise R6 loopback 10 through 12. And we're going to this time verify connectivity between R6 and switch 1 loopback 10 through 12. So before, actually right now we have that interface on R7. being a member of VRF-C1, so now we're going to change that to be a member of VRF-C2, and then also configure OSPF area 4 between R6 and R7, so that way we can advertise the R6 loopback interfaces as part of the VRF-C2. So at that point we should have reachability between R6 and switch 1 over here. That's also in the VRF-C2. Okay, so again, begin our configuration on the router R2. And to enable MPLS label exchange and forwarding, we're going to use LDP on this VLAN right here, 72. So on the R2 side, we have to enable LDP on the subinterface.72 with the MPLS IP command. Okay, then we get under the routing process, OSPF 1, and then we are dealing with VRF-C2 here. So remember, when you configure OSPF for the VRF, you have a separate routing process instead of using the address family. So VRF is actually defined as part of the router OSPF command. Next is the router ID, which is going to use 0.2. Always do passive interface default, and then we'll do no passive just on the interface that we would like the OSPF to run. So that would be fastest 0.72, and then enable OSPF with the network command. That will be .72.2. Be specific, so quad 0, and then that's going to be a part of area number 4. Okay, don't forget to redistribute, because since we're dealing with two different routing protocols here, we need to redistribute BGP into OSPF as well as OSPF into the BGP. Okay, so we distribute BGP 100, and then if you want out the subnet, which we for the most part do, we'll give it the subnet option at the end, the metric, which is going to leave it default, so whatever metric gets communicated across as part of the BGP advertisement, we're just going to transparently carry that over. Okay, now with the router BGP 100 address family, IPv4 VRF-C2, now we're redistributing from OSPF to the BGP. Okay, and we're just going to use the default metrics and everything. Next is our router R7. First thing is adding or enabling LDP on the interface, so MPLS IP. That's actually R6, my bad. So R7 right here. MPLS IP. And then right now, let's do a show run. You can see that the LDP neighbor came up on the VRF-C2. Now we do show run interface serial. Let's see what we have. Still, right now is forwarding C1, but we want to change it over to C2 and then put the IP back in, make sure we can ping as part of C2. Okay, we might have to wait for a few seconds there, just like last time. There you go. And then we create a OSPF routing process, so OSPF 1 VRF-C2. Similar set of commands with router ID 192.168.0.7, passive default, no passive, fast 00.72, so that's facing router R2, and then we also want to do a no passive of the serial interface facing R6. There'll be 0/0, and then enable OSPF the network command 72.7, area 4. And then the other one would be a 67.7. You can see we got loading to full already with R2. So we do show IP OSPF neighbor. You see here we have a state of full of the fast 00.72 with R2. Okay, if we do show IP route VRF-C2, you can see that we really expect the R7 to learn the switch 1 loopbacks by now, since we have the adjacency OSPF that came up. But somehow we need to look at the routing protocol. We are not seeing any OSPF routes. But if we do show IP OSPF database, you see how those 10.10 subnets is actually sitting in the OSPF database, but somehow it doesn't get installed into the routing table. And the reason for that, if you remember from our previous video where we did the PECE routing with OSPF, there's a concept of down bits. So when the routes are redistributed from BGP into OSPF as part of the MPLS VPN setup. The routes that gets injected into OSPF, all of them has the down bit set if they are LSA type 3, or if they were LSA type 5, we'll have the main tag. But here, since we are dealing with inter-area routes, it will be a down bit. So if you do a show IP OSPF database and then look at the summary routes, so summary being the LSA type 3, you see right here every single route. So these, for example, switch 1 loopback 10, they have this downward set, which is the indication of down bit. And that's why the router R7 does not install those routes as the loop prevention mechanisms into its routing tables. The way to get around that when you are dealing with the scenarios like this is to tell the router to ignore the down bit and go ahead and install those routes. And the command that you need for that is capability VRF-lite. Okay, so enter that, and now if you do show IP route VRF-C2, you see that R7 just basically ignore the down bits and then went ahead and install all those routes that belongs to switch 1. Okay, and those routes came across as the IA being the inter-area routes. Okay, so it's something that you kind of need to remember when you deal with OSPF in the multi-CE or in the multi-VRF CE situation. So R7 should be all set. Lastly is our R6. So go router OSPF 1, router ID 192.16.0.6, passive default, no passive, serial 00, the network of 192.16.67.6, area 4, and then we have to advertise all of this loopback. Area 4, so that loopback 10, loopback 11, and then loopback 12, where we can see that we have the OSPF adjacency that came up. So now if we do show IP OSPF neighbor, we should be seeing R7 being the neighbor of R6. And if we do show IP route OSPF, you see the R6 are now learning all the switch 1 routes. Okay, same thing if you jump over to switch 1. This point of the show IP route OSPF, hopefully switch 1 are also seeing routes that belongs to R6, which it is. So right here, all of them came across as the inter-area routes. So now if you're trying to ping from switch 1 to R6, 6601 sourcing from this loopback 10. Okay, so it took a couple pings, but eventually went through, and then after that you can pretty much source it from any interface, and then you can ping pretty much any interface between switch 1 and R6. And now that we have the connectivity between switch 1 and R6, that should complete our task number 3. And as you can see, that enabling multi-VRF support on the CE device is not that difficult, especially if you already understand the concept of VRF-lite, but you just need to pay special attentions in case you run these two routing protocols like BGP and OSPF, since they each have their own special requirements, as we saw in this lab. But if you were to run a routing protocol like EHRP, then there shouldn't be any special requirements for those. So you just go ahead and configure the routing protocol with the address families, and then make sure you enable LDP between the PECE links, and then you should be good to go. Okay, so that wraps up our video on MPLS VPN multi-VRF with the CE device. You can visit our website to view an extensive list of our lab videos and sign up to get access to additional lab contents. Thank you for watching LabMinutes.com, and I'll see you guys in the next video.